All right. So yeah, great. How is everyone doing? Yeah, welcome to lecture 24 of CS 545 or CSI 545. So today we will be talking about dynamics. So today and the next class we'll be talking both about dynamics and how they relate to simulators because they're very closely related. So what I'll try to do for today is give an overview of the technical foundation, and then we'll go through some of the computational examples because, I mean, they involve a lot of algebra. So I have about 6 pages of algebra that we can go through. I don't know how much we'll go through, but I just want to give you like a sense of the calculations involved, and then hopefully if it's something similar that you see on your own, then you can do something similar. So there will be some chalkboard stuff. So I don't think it will be easily visible on the recording or in the back of the room. So maybe if you have like a magnifying glass, you can look depending on how far back you are. So, all right, but anyway, logistics. So we are grading homework 3. So I think everyone has submitted that. Lab 3 had been released. I think there was an in-person thing yesterday, and then there's also another one today after class, and then I think tomorrow. And yeah, Lab 4 is also released, as well as homework 4. And then both Lab 4 and homework 4 are due April 26th. The main reason is after that, then you probably want to spend some time reviewing for the final exam on May 1st. So you can use two cheat sheets for that. So, if you want to reuse your first one, then that's fine. I mean, if you threw it away in anger and frustration, then make a new one. I don't know. Yeah, then for homework 4, everything you need to know for homework 4 from the class is from Monday lecture. I'm going to get the YouTube recording up soon. Any logistical question? All right. All right, so today and also next week, we will be talking about dynamics. So the first thing you might ask is, why do we study that? So when we talk about the dynamic, what we mean are trying to characterize the equation that describes the motion of a robot. So as you might imagine, the things are most easily done when the robot is simple. And then when it gets more complicated, you have to use like automated software to handle it for you. But taking a step back, the motivation is if you know how a robot moves, then presumably you can code that up, and in a simulator, you can then use it to test and debug your robots before trying them out in real. And yeah, then next class we'll talk all about the sim to real stuff and how that might work. But that assumes that your simulator is at least not terrible in accuracy. Like there's always going to be some simplifying assumption that your simulator will make, but we have to start somewhere. And then we will be starting today about how the types of simulators and dynamics models are developed for simple robots. So, and yeah, we will be talking about things like forces and torques, as well as a Lagrange formulation of equations of motion. So we'll discuss how to characterize that and the advantages of just using that over, like, say, analyzing it versus Newton's equation, where you have to consider all possible forces or force vectors that could happen on like any part of the robot. So when we talk about things today, the language that we will use is based on stuff from mechanics. So if you're familiar with that, like that might help, but if not, we'll try to make it as clear as possible. So the terminology that we'll be talking about a lot today is called generalized coordinates. So generalized coordinates are just some way to describe your the configuration of some robot. And the word generalized suggests that it's a generalization of your usual meaning of what a coordinate means. So when people talk about coordinates, we often talk about Cartesian coordinates, like this is the X position, this is the Y position, this is the Z position, but you can describe your robot in different ways. Like maybe it's more convenient to state like what is the joint angle 1 and joint angle 2. And if those characterize the position, then it's another way to describe the configuration of something. So that's what we mean by that's what generalized coordinates mean here. And again, generalized coordinates must uniquely describe a configuration of your system. So in robotics, it's very common that they're joint angles. So we talked about revolute joints, we talked about prismatic joints. So like revolute ones are very common in robotics, like you have two robot links and then they're joined by a joint, and then you have some angle that describes the location of a link with respect to another link. All right, so we have the notion of generalized coordinates as well as generalized forces. So as you might expect, the generalized forces are one way to think about a generalization of, like standard, force vectors that operate on some body. So a generalized force is just a way to denote like some set of forces that apply on the generalized coordinate. So you might have a bunch of revolute joints or prismatic joints, and then the generalized force would be like the force that is applied on some joint to like make it move. So if you have a prismatic joint, then that means you have some joint, and then there's something in meters that describe the location of one with respect to another one, and as like the meters go up, then the link seems to get farther and farther away from the parent link. Then you would have your delta times Q be in meter, and then your Q unit would be in like Newton. Yeah. So again, again, these things are just general concept. Like you can have different robot systems, and then there will be different types of generalized coordinates and forces. So when we look at some examples today, you'll have to think about, why do we decide to pick the generalized coordinate as well as the generalized forces? So this is just a general recipe, and then you have a new robot system. You have to try to think about how can you describe it in this framework. And yeah, we came all the way today without we came all the way in this class without talking about work at any point, I think. So, work is I just took the description from Wikipedia. So it's like the energy transferred to or from an object by the application of force along a displacement. So you can think of this as like the work done, which is the sum of all the generalized forces times a small change in the generalized coordinate. So again, a generalized force corresponds with a small change in its coordinate. So here's an example. And this example is not really robotics related. It's just a way to think about what's an example of a way we can describe something with naive coordinate versus a generalized coordinate. So suppose we have n particles. So they might be point masses in 3D space. If the particles don't have any constraint, then we can uniquely describe the state of the system with 3 times n coordinates. So 3 numbers per particle, right? So you have position of particle 1, particle 2, and so on. And the most straightforward way of describing the coordinate would be with all the position of the particle. So R1 all the way to Rn. If we are able to apply some force that acts upon the particle, then these would be Newtonian forces that we would indicate with 3D vectors. So you have a bunch of particles in 3D space. Each one has a 3D vector that shows like where is the force that acts upon it, right? So we would mark that as F1 all the way to Fn. So just think of this as, this is some system, and then we can apply some force on it. Another similar example would be, we have some robot that consisted of a bunch of links. We apply forces on each of the joints that connect two links. But this is not even a robotics example. It's just trying to make the idea of, coordinates and generalized coordinates versus forces and generalized forces clear. Yeah. So if there are constraints on the point method, so let's say there's k constraints, and each one is this particle and this particle must be a specific distance from each other. And if they're independent, that means they cannot be described by a combination of like other constraints. So I think we talked earlier in class around like lecture 12 or so on the informally, the number of degrees of freedom of a system would be the sum of all the freedoms minus the number of constraints, or really the number of independent constraints. So, you can arbitrarily add in more constraints, but if they don't add in any restriction, it doesn't mean anything. So. All right, any questions about this setup that we'll use for the first example here? Yeah. Can you describe R here? So this R is just notation that describes, position. So maybe we can write it out. So like R1 equals R1 X. So this might be the position of some particle here. And then R2 might be some other particle. And then, R3 and so on. Yeah.
That's because it's a 3D space. So we have X, Y, Z.
Well, yeah, because we're assuming that the point masses are in 3D space. Yeah, but we're really referring to a system of particles. So when we're trying to describe the system of particles, they actually live in a 3 times n dimensional space. So this is a 3D space with particles, but to describe all of them, you need a vector in R3n to describe everything in the system. So if you have constraints, then one constraint would be, so if you have 2 points, then the distance must be fixed, then that adds another constraint. That adds a constraint to the system. And when you add in constraint, that means the dimension of the whole system, the number of dimensions or the number of numbers that you need to specify every unique configuration of the system will decrease. So if there are k independent constraints, then you can use 3n minus k numbers to specify everything. And that's what this notation means. So this notation here, what it's trying to do is describe the system, but in a different way. So this is trying to now describe the system in a 3n minus k dimensional space, where this should be capital K, and where these are now considered our generalized coordinates. So if you notice what this means, so Q1 and all of these numbers, they don't necessarily correspond to like position of particle 1, particle 2. They're just numbers that denote what you need to describe the whole system now. So instead of all the R's, you now describe the system with Q1 all the way to Q3n minus K. So these are just some like the exact implementation of these functions. That's not really critical here, and I don't know the details of how those would be implemented. All I care about is we used to use 3n numbers to indicate the space. Now we've added in constraint, and then we just rewrite everything in terms of the Q. So those are the generalized coordinates. So that makes sense because I found the concept to be a little bit trickier than I thought it would be at first. All right, and this example, yeah, this is a common example that you see in like some physics or mechanics courses. So what is going on with these equations is it's trying to show the amount of work that is done on the whole system, first expressed in your normal like Newtonian forces, and then at the end is re-expressed in terms of generalized forces. The exact meaning of what each generalized force is, I don't actually know. All I know is that it's just some other type of force that we could apply, and it's just a way of rewriting or re-expressing how we how we describe what work means. So one way to think about this is or maybe. So each particle in the system has a force vector that acts upon it. So each of these is a 3D vector. So this notation here, what it really means is a dot product. So that thing is maybe. So that's what the first term is. It's a sum of a bunch of dot products of the 3D forces and the small change in the position of each of these based on the application of the force. So what's going on here is a rewriting of this to express it in terms of QJ, like the generalized forces. So the way that this works is you take each of the change in the delta Ri, you can, you kind of see what's going on here. So if there's a sum over J from J equals 1 to 3n minus K, and then all the terms here are the delta QJ, right? And then just multiply by 1. It's a very common trick in math. So just multiply by 1. You have a bunch of terms here, then the 3n minus k is because you had 3n minus k terms here. And the reason is, and then when you have a set of sum and you have a finite number of terms, then you can rearrange the sum so that the sum over j goes first. And then this is just rewriting this as, the sum of I equal 1 to n of fi. That's a 3D vector with a dot product of delta Ri. That's a 3D vector with delta Qj here, which is a scalar. So the notation is a little bit, it could take some time to think about it, but hopefully I wrote enough detail because I ran into the question myself when I was trying to understand the system. So hopefully the explanation here helps. And I'll do the same thing for the examples that we talk about later. So yeah, this is just, and then here you just simplify the fi times delta Ri, the dot product of those again, divided by the scalar here. And then you get what is the Qj here? So that's a generalized force. So I think the bigger takeaway for me when I look at this equation is, we have the work from the sum of Newtonian forces, then we express the same thing, but as a sum of generalized forces. Now, the reason for this, you might ask, what's the point of this? Are you curious about that? Oh, you all think it's okay. All right. So I guess the point of this is that when robot systems become very complex, it turns out that trying to analyze a system in terms of all the forces like F turns out to be very hard. But when you write it in terms of generalized forces, it becomes a lot easier. And that brings us to this thing here. So this, these QJs are a way of writing out the generalized forces. Now, the advantage of this from this example is not totally clear, but I hope that this is going to give a little bit of intuition. To really dive deeply into this, I would recommend books like the Classical Mechanics and stuff, which derive this in a little more detail. So here we can only give like a high level overview. But the main advantage is because we can write out generalized, I think this should be generalized forces, sorry. So if you can write things out in terms of generalized forces, then you can characterize dynamics of robot systems using, energy principles. So like computing kinetic energy and potential energy, you use those to compute the dynamics instead of using a bunch of forces and acceleration to do the same thing to analyze the equations of motion. So what I'm trying to show here are the Lagrange equations where T, so T is the total kinetic energy of the system. B is the total potential energy of the system. Unfortunately, you'll sometimes see like people use U for potential energy. So as long as you understand the context, it hopefully won't be too bad. So again, I'm not gonna these types of equations, they're derived from some other field. Like if you look online, there's tons of resources about how do you derive these equations. I think for this class, we're just gonna assume that you can write out equations like that and then make them equal to your generalized forces. And then from there, we can start analyzing systems of motion for a robot system by following a standard recipe that involves compute potential energy, compute kinetic energy, compute the derivative, then partial derivative, then we're good. So, Yeah, so it's very mechanical. So you just have to figure out like how do you compute T? How do you compute L? How do you compute the generalized coordinate and force? And then you apply a standard recipe. Yeah. Yeah. And again, the main advantage is you can write equations of motion by using energy principle instead of forces and acceleration. Yeah, any questions about that? I think we'll go through some examples. Yeah, we'll go through some examples. So, so yeah, while we're gonna start with simple particles first, when you get to robot manipulators, what we want to do from here is deriving these sets of differential equations that describe, the motion of the robot. Once we have that, you can code it on a computer, then you can simulate it. Yeah. So that's the whole reason for analyzing this. If we don't know how to do this, then it comes, how do you simulate the robot? Yeah. And to obtain Lagrange's equation for a robot manipulator, you calculate the kinetic energy and potential energy of the robot's length as a function of the robot's generalized coordinate. I mean, yeah, if we're talking about particle system, then we don't have like robot length, but the same concept of compute kinetic and potential energy also applies. All right. So let's do a few examples to try to ground what we were just talking about into something that's a little more concrete. So we have one particle that can only move in one dimension. Yeah. So is there any that's about as simple as a system you can get. So when you have a 1D particle, so are you familiar with the formula for how to derive kinetic energy? So if you have like one thing and then with mass m and velocity v, then the kinetic energy would be 1/2 times m times v squared. So you can look on standard references about what that means. And often we're, at least for notation wise, to make the notation here is really awful if you're trying to compute derivatives and partial derivatives. So that's the reason why I have 6 pages of math here that I can look at for today. So to make it to not make it worse, we have the dot notation. So if, like all of these x's are a function of t, right? And then when you do d over dt of xt, then we write it as x dot, right? And then when you do another d over dt, that's acceleration. So we write 2 dots. Yeah. But you should think of the x's as being functions of t. So I find that if you're looking at this for the first time, like it might not be clear like what is functions of t and what is not. And then when you apply derivative, maybe it's not clear like when should you when can you use the chain rule and so on. So that part I found to be a little bit confusing when I was going through the math. So hopefully it's going to be a little bit clearer, when we work through things out. So yeah, this is one 1D particle and 1D. When we're trying to analyze the equations of motion, we remember that we wanted to get this thing here, right? We wanted derivative with respect to time of the partial derivative of the kinetic energy with respect to the generalized coordinate. And here the generalized coordinate is something straightforward. So because it's a 1D particle in 1D, you only have the x coordinate, okay? And then we're going to make the x equal the q. And then we only have one generalized coordinate here. It's that thing. So it cannot be as simpler as this. So we can compute the partial derivative of t with respect to dot q here. And then when you do that, you apply the standard derivative, you pull the 2 down, it goes away, and then you get m times x. You can take another derivative, and then you get m times double dot x. Yeah. So are you familiar with F equals ma from like Newton's equation? Like that's basically what's going on here. So there's no gravity here. So for this example, we assume there's no gravity, which is not a realistic assumption. So we're going to make it a little bit simpler in this next example. So imagine that we have a 1D particle that's moving in 3D. So you have a single point mass, it can move anywhere in 3D, and we can apply some force vector on it. Now the generalized coordinate that we're going to use, because whenever we do the Lagrangian analysis, we have to decide what are the generalized coordinates we're using. So the generalized coordinate in this example is just going to be the x, y, and z position of the particle, because that makes the most sense for these types of systems. So what's the kinetic energy of the particle? So if you look at this equation here, we had 1/2 times m times the speed of the particle. And then you can write it out like this, where you have 1/2 times m times the velocity squared in the x direction, and then the y direction, and then the z direction. So this is how you would write a kinetic energy. In terms of potential energy, again, this is something that I think comes from classical physics. So if you remember how to compute potential energy, you would take the mass of something times its height times what is g? Yeah, the gravity, right? Gravity, right? Like minus 9.8 or something like that. Yeah. I only know up to minus 9.8. I don't know what comes after 8. Yeah. So we have kinetic energy, potential energy, and the Lagrangian that we talked about earlier, that's the L equals T minus V. So kinetic energy minus potential energy. So we're just writing it out like this. Now, when we compute the generalized forces, remember that we're going to be using these equations. Now, these equations come from the formula that we talked about earlier. So if you remember, we had to talk about d over dt, the L over dqi, right. So we had this equation from earlier. This thing here. Yeah. And by the way, if I miss any dots or something, please let me know, because it's very easy to make a mistake when writing out the algebra. So this type of equation is how we would start, is what we would do to try to compute a generalized force. Now, in this example, the generalized force is actually the same thing as your naive force in the x direction, y direction, and z direction. The only reason why we're doing this is to check that treating things in terms of this produces the same thing as if we were to analyze this with Newtonian physics. That's the reason why we're doing this example. Because if it didn't work, then it would be very strange. So when you do the math, I mean, the math is pretty straightforward. yeah, you have t minus v, and then like the partial derivative of L with respect to x dot, that would just be the 1/2 m times x dot squared, and then the 2 goes away when you pull it over, then you just get m times x, and there's nothing here, so that goes away. And then you apply d over dt, and then that turns it into mx double dot. Yeah. And the only thing that really, the only main thing that's different is the fact that for z, we have this term, the partial derivative of L with respect to z. The z doesn't appear here, but it appears here at the end. So minus m times g times z, then the z goes away, then you get mg here. So from this example, we see that when we analyze this using Lagrangian equation, we end up deriving generalized forces that are actually the same as Newton forces. And it makes sense that the force is going to be, the force in the x direction is equal to like the mass times the acceleration in the x direction. Same thing for y and z, where for z, we also have the gravity to consider. So. All right, any questions about this example? Yeah.
We talk about how the equation response is one.
So are you asking, given these equations, how do we implement them in the simulator?
Yes.
All right. You can, all right. So you can have whole courses on how do you go from equation to actually implementing it in a simulator. So I think the answer to your question is very, very long and deep. So I have to think about how to make it, how to answer that in a way that I can describe in like 2 sentences. So I think the way to think about this is you have your equation of motion. In simulation, you would do like a time discretization. So like you try to discretize a system into smaller time steps. So going from time step 1 to time step 2, you use this equation to change the system that's in simulation according to these inputs. And there are like equations that you can use to sort of integrate physics steps based on these equations of motion. So I think again, I think it's very tricky to answer your question because it's such a deep question. I think it's something maybe I should bring it up in next class, like the more detailed steps of going from these equations to like coding in a computer. If you want that, I can focus more on that for next Monday's class. Yeah, I think. Yeah. Question.
Yeah, I was just curious as to why the Lagrangian consists of the kinetic and potential energy. Like,
So is your question, why did the Lagrangian have the kinetic and the potential energy?
yeah, like why those,
Oh, why those two? Why those two
why
terms?
those two energies basically?
I guess. Yeah. The best answer that I can give you is, I think if you know the kinetic energy and the potential energy of a system, then it feels like that, like if you know the potential and kinetic energy at any instantaneous time, then you kind of know like how is the system going to change. I think that's the main intuition here. Like maybe kinetic and potential energy is enough to describe like how a robot will move. Yeah. So the kinetic energy will take into account the force that is applied on it. Like if I'm controlling a robot and I'm telling it to move its torques in some direction, that's going to be reflected in the kinetic energy at any given time. So that is my intuition. I don't know if others have better intuition about that. Hi. Hi, so we talked about a 1D particle, but it gets a much more interesting and then also much more uh, algebraically intensive when we talk about systems of equation with more than one thing in it. So this example is a classic example that's very commonly analyzed called the double pendulum dynamic. So this example, and you can find the reference from Russ Tedrick here about some of this, but the online textbook doesn't actually go through the algebra on like how to do it. And I'd like to show how it's done, just so you can see how it's done once, and then remember it once for here, once for the final, and then maybe you don't like do it again. I don't know. Or at least you code it up, and then you rely on your code to do it for you. So we have this double pendulum. So this thing is like the ground term, so it's like maybe some ceiling or whatever. We have theta 1 and theta 2. And this is how we actually apply the force. So you can apply a force onto the change like where link 1 is located and then where link 2 is relative to link 1. And the objective here is trying to derive the equation of motion for that, where we can use Lagrangian dynamics. So what that means is we need to go to these sets of equations, which then means you have to write out what is the potential energy, what's the kinetic energy of the system. And then we plug that into here, we do the differentiation, and then this whole thing will give us the equation of motion for each coordinate, for each generalized coordinate. And in this example, the number of generalized coordinates is 2, right? So we just have Q1 and Q2. So that kind of makes sense because you only need 2 numbers to specify the configuration of this double pendulum. So that's why you have 2 generalized coordinates. And then, yeah, unlike prior example, the generalized coordinates are not like your naive Cartesian coordinates. They're actually the first angle and the second angle. Yeah. And yeah, notationally, do you remember this from the inverse kinematics lecture? So you have to write it out as SI and CI, otherwise it doesn't fit on a slide. All right. So the way to try to do this is we first compute the kinematics of the system, and then use that to compute what's the kinetic energy and then potential energy, and then from there you can do the math. So the first step is writing out the kinematics of the system. So what P1 and P2 mean are, what do they mean? They mean the position of M1 and M2. And also, we're also going to assume that all the mass is concentrated in the M1 and M2. Yeah, because otherwise, you get into more complicated analysis. So the simplest way to think about this is inverted double pendulum, link of length 1, all the mass concentrated in M1, and then link 2, all of the mass in M2. Yeah, and hopefully the position, like the formula for position is clear. Like you would use trigonometry for that. So for P1, you would have to, write out your triangle, then you do your trigonometry, find the position of P1, which is position of where mass 1 is located. For P2, you would do P1 plus this thing, because you have to do like this thing, and then you can do your analysis from this. And then you have 1 plus 2 because you have to combine this angle with this angle, like when you do the trigonometry. Now, what about this? So this is showing the rate of change of the position as a function of time. Does everyone see how to compute like this, right? So I'm never, I wrote it out here. So for the first case, it would be P1. It's not bolded, but it's not bolded P, but it's the same P. So yeah, the way to get this is you take P1 and then you apply d over dt. So L1 is just a scalar. You pull it out. You get d over dt times sine of theta 1 and minus cosine of theta 1. The way that this works is you would apply it on every individual item here. So the sine goes to cosine, the cosine goes to sine, negative sine. And then this is the chain rule because all the theta terms are functions of t. So you would have d over dt sine of t. Right. So you have this. Or if you want, you can put in like a one here. Equal. Right? Gotta catch my error. Or sometimes I deliberately do it and check if you caught it. So if you're, so just making sure that you know what is functions of t is gonna make like deriving the equations of motion a lot simpler when you try to analyze it. All right, any question on this so far? Then we'll discuss computing the kinetic energy, potential energy, and then putting it into this, and then we get our equations of motion. Yeah. So again, the whole point is compute equations of motion from the kinetic and potential energy. All right, so why don't we take I think this is a good time to take a short break, and then we will get back to we'll get to the writing out the kinetic and potential energy. All right, so maybe we'll be back at 4:56. All right, so let's get started again. All right. So as a reminder about what we're trying to do is we have a double pendulum system. We want to derive equations of motion so that we end up simulating it. We have equations that we can just pass into our computer. So the recipe for doing that is find your generalized coordinate. That would be Q1 and Q2. Find your generalized coordinate, write out the kinetic energy, write out the potential energy, take the derivative that are necessary for the Lagrangian, and then you get your forces. So again, this example, if you want to see more details, you can look at this reference here. So I will also ask for your help. So I can go through all the algebra, but it can also, there's probably not enough time to actually write out every term. So if there are any equations that are not clear to you, maybe I should prioritize writing out those. So just let me know what part I should actually write out on the whiteboard, on the blackboard. Yeah. So I think everyone is clear on like these equations. All right, then. So this is our setup. So we have generalized coordinates, we have position, and then we have the change in position as a function of time. Now, using what we computed earlier, you can write out the kinetic energy and the potential energy like this. Now, this is, if you're wondering why this is true, then you can think of this as like a generalization of the kinetic energy formula, but in a vector form, where you have to take like the inner product of a vector with itself, and then because you have vectors, but you need to make it a scalar because energy is a scalar. Then you would do this math here. For next class, I'll go over like more about kinetic energy and then how you have to put in like the translational energy and then the rotational component in it. But for now, let's just assume that we can start from this equation for kinetic energy. And potential energy is your standard, mass times gravity constant, like minus 9.8 or something like that, times the height. And the height, because we just have a 2D system, we're just going to assume that we can use y here. So. All right, so is everyone confident that they could derive, like, do you know, like, why it simplifies to this and why it simplifies to that? Or is there a part that you want me to do? Because yeah.
Like, how did you go from and
So wait, do you mean go from here to here?
no, like the t given t equation, which is like 1/2 m times x dot squared plus y dot squared to that. So given equation.
Like, how do you go from, is it, oh,
How do you go from given these equations, how did you set and then given the equation from where G inside above?
oh, so how do you go from here to like defining T here?
Right.
Yeah, so I think the I think that comes from how kinetic energy is normally described for system, like you, because kinetic energy, all right, so there's a couple of things here. So kinetic energy would be the sum of the different components of it. So the first thing to note is you have two things here. There's only two things that have any mass. So those are the only two things that must contribute to kinetic energy. So you have the 1/2 times the mass thing. Now, because you have two things, you have to sum them together. So that is 1/2 times mass of one. Plus, all right, you have 1/2 mass of one times something, plus 1/2 times mass of two times something. All right. And then what this is here is the P1. All right, so my intuition of this is that these P's are like characterizing your change in the position. So those are like the velocity terms. And because we are dealing with vectors, we cannot just square a vector. The way to deal with that is to take the inner product or like dot product of a vector with itself. So that is how I think of it. I think there's maybe there's a more principled way to derive that, but this is how I think of it. I'm gonna I've already marked that as a note to myself to explain more about that in next class too. So yeah, but if you believe that you can derive T that way, then you can do the rest of the calculation. So when I look at the textbook, they don't justify why, they just gave the T to me. So
Go to the second line. Are we just substituting the equations given in the slide for each?
yeah. Yeah, so we are substituting. So for this, you have P1 dot and P2 dot, and then those directly go in here. And then yeah, if you do a bunch of algebra, you'll get this. Plus or minus a few terms that that, so yeah. Oh, what about this thing?
Yeah.
What do you want to know about that? All right. You want to just go over what that second term is? So this is, I'm sorry, I only have so much room that I can write here. So yeah, 1/2. I didn't, wait, 1/2 and 2 P dot. Yeah. All right. Oh, yeah. This is, it's a little bit, it's a lot here. So 1/2, oh, wait, this is M2. Yeah, M2. Two times. And then you have the same thing here. I ran out of room already. So this thing. Yeah. So yeah. Yeah. P1 dot plus L2 Q1 dot plus Q2 dot. Yeah. Yeah. And then when I go from here to here, have to so this so when you go from here to here, you have this 2D vector, then another 2D vector. You sum them, get a 2D vector, then you have a dot product with itself. And so the first thing is you have P1 dot transpose P1 dot. That simplifies to this because yeah, you have P1 dot, which is L1 and Q1 dot here, then you square that, and then you get C1 and S1. And then you have a dot product with itself. That's the same thing as C1 squared plus uh, yeah, plus S1 squared. And then what is cosine squared plus sine squared? Yeah. 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 So when you do these calculations, you can see that term come up a lot. So go on. And then the next thing that you get is this term multiplied by the like this thing transposed with the same thing here, because you have this plus that. So this part will turn into you know, L2 where you're Q1 squared plus all right, so this thing comes up again. So you get another cosine squared plus sine squared thing. Yeah. So if that's not clear, the reason why is you have one term here, then you have another term here. I'm just doing that. You have two terms transpose two terms. I'm doing the first time the first, the second time the second, and then we'll do the first time second plus the second time the first to simplify this term above. Yeah. Yeah, this thing goes. All right. Well, yeah, P1 dot. So, all right, so going from like this term is going to simplify the whole simplifier, like turn into this thing here. It's mostly just an application of your, a matrix algebra and like simplifying a bunch of the cosine squared plus sine squared. Yeah. It's mostly elementary algebra. You just have to be very careful with notation and stuff. Then after that, we have to simplify this thing here. So this thing is yeah, that's one. Yeah. Yeah. This whole thing is just cosine of theta two. So do you see why? Can I write it over here? I'll just write it over here, just very quick. I know, people on the recording can't see it, but I prioritize the inside experience. So. So this thing here, this comes from the cosine identity of cosine of theta one plus theta two, or T1 plus T2. And then there's an identity to rewrite that in terms of this. So the main thing here is just to account for cosine of A plus, no, A plus B, and then sine of A plus B, there's an identity of it. Is there a typo comment?
Yes, sine one cos, sine two, one cos two, two, shouldn't it be like a plus sign there?
Oh, really? The thing. I wouldn't mind it in my knowledge.
I
Yeah,
figured,
double check what, yeah, just search what is the identity of sine of two things, A plus B. Yeah.
yeah, so plus,
Oh, there should be a plus here? All right. All right. Yeah. Oh, there should be a minus somewhere. Oh, wait, there is a minus here. There is a minus here. I think we're good. Yeah. Yeah. Well, this minus is high. All right. All right. This is yeah, that thing's the same thing. So this thing, that thing will go away. And then you get this plus that. So. Oh, me too. Yeah. So that's why I wrote in this because I didn't know why the C2 was there until I thought I remembered the cosine and sine identity. So that's why I have this note here. Yeah. And sorry, I don't have the Google Doc with the because I thought most people weren't using it, so I don't have the Google Doc with me. I can. Yeah, yeah, yeah. All right, then maybe taking a step back. What this is giving us is we have the Q1 Q2 Q1 dot plus Q2 dot plus C2, right? And then you get Q1 dot, and then you get L1 and then L2. And then the math comes because the 1/2 M2 comes in, the 2 goes away, then you get, so this whole thing that appears here. Yeah. Now this part and this part, they'll appear. Yeah, that one will appear over here. So you have 1/2 M2 with this part. That will go here. And this thing here is going to be merged with this thing here from P1 dot. Because we only expanded out the second part here. Yeah. Again, I mean, I can go through that more, but like I've already run out of room for the entire thing. So I just want to focus on the algebra that's maybe the most trickiest. And then the rest you can fill in the gap when you look on the look at the textbook online. Yeah. All right. Any other question? Yeah. Question?
What is the high level of intuition?
So what is the intuition of using the Lagrangian here? I don't know if this is going to satisfy you. My intuition is the second point here. So this second point is my intuition here, and the intuition here is we only have to know if we know t and u, then the next thing we can do is take all the derivatives and then we plug it into the Lagrangian, and then we have our forces. So the intuition is it's a very mechanical recipe. Like there's a lot of algebra, but it's a very mechanical recipe. Find your generalized coordinates, compute your kinetic and potential energy, compute the derivative. You substitute it back into the Lagrangian, and then you get your forces. If you don't do that, then it's less mechanical. Then you have to think more about, I don't even know what to think about it because like it's not a mechanical recipe I can follow. This is more a mechanical recipe that I can follow. Yeah. Question?
I was actually gonna address what you said. I was thinking more along the lines of that the intuition could be that the potential energy in a way is always constrained by the kinetic energy. And the kinetic energy is also constrained by the potential energy because it's like, so that's where the Lagrangian could maybe come into play because both of them are constrained by each other.
Yeah, I guess they are both constrained by each other, and yeah, maybe that is one way to think about it. All right, well, so I think if you accept that these are the kinetic and potential energies, then the next step is to just compute all these derivatives. I mean, you might think, yeah, it's a lot of work, but in practice, you're using a computer for it. And there's a mechanical recipe to follow. Like that's really important because if you have a different robot system, then you can try to specify the energy and then just plug it into the same code that will compute the derivative for you. I mean, these are complicated, but deep neural network, the gradients involved are much more complicated than this. So, all right. So I'm on these equations, just maybe just look at them, and if you want me to go over any of them, I can pick where I can search for where I wrote it, and then we can derive it. We should probably go over at least one of them. Just and also, do you see why we have to compute these? Because Oh. Oh. So this is the thing that we want to compute. But you have like L equals T minus, I think it's U in the case, yeah. U, yeah, so. You have this is the Lagrangian that we want to compute. It equal to T minus U. So that's why when you distribute the partial derivatives in, like you get all the like intermediate terms. And so when we can, like, if we can find all these terms, then we know like what to compute here. Like this is just like E over D, this thing. Yeah, like that's just how you simplify it using L equals T minus U. Yeah, so all these terms like they come up here. All right, which equation do you want me to do? Maybe try not the most trivial one, but not the most complicated one either. Hmm. Or if you want, I can pick one of them. I mean, so did anyone want me to do any one of these? Let's do one of them. Let's do one of them. But I don't know which. I want to use the one that would be most beneficial to you. So maybe let me look. So maybe we can try. Maybe we can try this one. dp partial derivative of t with respect to q2. I'll go over there. All right. What is t? All right. Well, what is t? So, what? So I'm only going to keep the terms that depend on q2. That would be That would be this one, right? So this thing here is equal to cosine of QT, right? Then when you take the partial derivative, this is the only thing that changes, right? It goes to sine and then you put in a negative. And then. Yeah. And then you get. Yeah, that was it. So again, the algebra here, the only tricky part is keeping track of everything and understanding that Q2 is the generalized coordinate for theta 2. And then you have C2, which is cosine of Q2. So this is the only thing that is a function of Q2. You have the Q2 dot, but that's a different variable. All right, so this is just one example of how to do one of those. You just do all the others, and you can kind of see how to do that. All right, any question? Yeah, so remember, the whole point is you compute those, and then you can plug everything back in this equation. All right. Now, given all the stuff from the prior slide, you plug those terms into here. So you plug the terms into here. And then you get your equations of motion. So if you look at the textbook, it'll literally just write out, d over dt of this thing, and then it uses the prior stuff, plug them in, and then with some algebra simplification, you get this thing. So you get this thing equal T1, this thing equal T2. So those are the generalized forces, the one that we talked about earlier, the generalized forces that are applied on the first joint and the second joint to determine like what are theta 1 and theta 2. And if you know like what this equation is, you can decide like, what are the like inputs, like you can input things like, again, like you can pick stuff to input, like, different, Q term, and then you do the formulas here, then it describes like where the robot should move, basically. So yeah, I think if you look at the reference, like they basically end at this point saying, you implement these in a computer, you get your robot simulator. So again, it looks very complicated, but the actual process is very mechanical once you can compute kinetic and potential energy. And for a computer, that's all that really matters. It just has to be very systematic about how do you describe something and how to describe the way the system changes. So, do you want me to compute? Do you want me to show how some of these are like derived, or do you want to skip to like the next example? Yeah, what? Oh, yeah. So I think, okay, so go through the math, go through the algebra yourself. see how far you get, see how close you get to here. And then if you're off by 2 or 3 terms, then we can talk about the specific part that might be missing. Yeah, maybe that, I think that's good. The only way to really understand, the main way to understand that is to just go through it and see if you can match the algebra here. So there is a pattern to this. So when you look at the example that we just talked about, and when you also look at other examples of simple robots, you can see that there is a pattern to the equations of motion. So the first thing is that you can see that the kinetic energy of a robot system, you can write it as follows. So you can write kinetic energy as T equals 1/2 times Q dot transpose. So the Q is almost always like the joint angles of the robot, like the configuration vector, basically. You get Q dot transpose times, this is the mass matrix. Q dot here. Yeah. So kinetic energy must be non-negative. What does it mean to have negative kinetic energy? I'm not sure. So, well, that means that this must be a positive, at least positive semi-definite. Then it also means that an inverse exists. So you'll see in the next class, you can apply an inverse, and then that means if you want to be at a specific configuration, you can apply your inverses to determine what are the forces that you have to do to get to those positions. I'll try to talk more about that next class. In addition to how to simulate this in a computer, and then more on like deriving kinetic energy, more examples. So. Now, building upon that, this equation here describes what are the manipulator equations. So for any general robot system, you can write out your manipulator equation in a very systematic way. Now you have to pick values of, you have to pick like what are C and what are B and so on, but you can find values of those that you can put into this equation. So this equation tries to relate things like your mass matrix times the acceleration of the joint plus the C matrix, which is dependent on your joint angle and then their velocity. This captures the Coriolis forces. So you have the mass matrix and then the Coriolis forces equal to the gravitational forces plus the, so U is like your controlled, and then B is a matrix that maps into your generalized coordinates. If your controls are the same as your generalized coordinates, which makes more sense if you're talking about a simple robot, then B is the identity matrix. And you can think of this equation as the mass equals the forces here. Yeah. Although I don't know why usually people put the C matrix to the left-hand side, even though you can argue maybe it should be on the right-hand side, but And then if you have other forces like friction, then you can add in other terms. So friction might be if you have 2 robot links, but then there's some friction involved that causes their motion to be not modeled fully by this equation. Yeah. But again, this equation is just a model. So, it could be wrong, but for many robots, it is a good fit when you combine good math matrices and the Coriolis matrix. And in software such as Drake, so Drake is a robot simulator, and the way it works by simulation is you define values of like M and C and B, and then the simulator will just handle the physics for you after that. Yeah, then the first two term will contribute to the kinetic energy of the Lagrangian. So again, I think the way to understand this is to look at a few examples and see how do you define what are like math and Coriolis matrices for a given like robot system. So I think I have an example of that. Oh, well, actually first I have this video of the Coriolis force. It was from by Stefanos shared me a video of this, and then you can do things like measure the Coriolis force. So it's a way of like showing that there must be some, when you're rotating, you have to consider forces like if you're further away from the center of rotation, you end up moving a greater distance if you're like rotating about it. So uh, I'm not gonna play the video, but you can at least see it. The link is over here if you want to look at it. I mean, if you look at the YouTube comments, they say things like, "Oh, you gave me a better understanding of Coriolis force than my entire physics class." So you can. Personally, I found the physics class to be more informative to me, but some people like the video. Oh yeah. So this is describing our double pendulum, but in manipulator equation. So again, we talked about how you have the general robot manipulator, you can write them out like this. And whenever you write things down in a systematic way, that makes it easier for software to handle different robots if you can express them in a standardized format. So if you remember the equations of motion here, like this whole thing, you can take that, you can take the whole equation and then plug them in here. And when you do that, you end up getting the same thing as earlier. Uh, the one thing that is different is that you have the B and U here. But that is just something extra that you can then add an extra force. Uh, so. Yeah, then you see that the B matrix is the identity because it's just simpler to think of the forces acting the control of U directly acting on the generalized coordinates instead of having another matrix change thing to. All right, is there any question on this, or do you want me to go through the matrix algebra here, or do you think it's better to do it on your own? All right, so you can try it yourself and then just do the matrix algebra and see if you derive the same thing. Yeah, I think that'll be pretty good. Yeah. All right. So there's another example here. We're not going to go through the whole algebra because I don't want to do this all day. So the carpole is another classical example of a robot system that has been analyzed a lot, and it's simple enough that we can write out the equations of motion just like the double pendulum from before. So you can derive the equations of motion. You use the Lagrangian dynamic, which means what? You find the kinetic energy, find the potential energy, compute the derivative, plug them into this equation. You get your equation of motion. So the way to think about this is you have the carpole here. The carpole has mass MC. It's a little bit hard to see on the slide, but it's MC, which is the mass of the mass of the carp. Then the mass of the pole has MP here. So the only mass is concentrated in those two. But when you write out the kinetic energy, it's only going to contain like those two masses. Now the x coordinate is over here. The angle is theta here. So the generalized coordinate would be what? The x and the theta here. So that's the generalized coordinate. So remember that in the double pendulum, the generalized coordinates were theta1 and theta2. So here we're going to make them x and theta. Yeah, so like often the first step here is identifying what is the generalized coordinate. And then you start the analysis from that. And the task is to stabilize the unstable fixed point at x equals 0, pi, 0, 0. So the confusing thing here is I think x here is a four-dimensional, four-dimensional vector that includes a 2D q and the 2D, q dot. But the x1 and x2, they refer to the position, like this refers to the position of the card, and then x2 is the position of the pole, the top of the pole. And this is the task. And this makes sense because when it's at 0, pi, 0, 0, that means the x is at 0, so you're located here. And then theta is pi. That means because theta is 0 when it points down, when it's pi, that means it points up. So that means the card pole is pointing up. And then the change in x and the change in y is 0. But that means it's not changing. So this is the task. And this describes the kinematics of the system. Any question on the kinematics of the system? Yeah, like with x1, the position is just the the x coordinate, and then the 0 is because it's staying the same height. So there's no height involved. And then x2 is the 2D position of the tip of the pole. And then you would just do your trigonometry, and then you add an offset of x. All right, so I'm skipped ahead of some of the algebra here, but the high level idea of how to solve this is you write out your kinetic and potential energy. Now, the way that the kinetic energy here is, it consists of, so the general way of to compute the kinetic energy is that there's translational part, there's rotational part, and then there's inertial part. I'm going to go through more of that in next class. I'm going to try to go through how to compute the different parts of the kinetic energy. But if you accept that this is the kinetic energy, and if you also think that this is the potential energy, then you can compute your partial derivative. You plug them into your Lagrangian, like this thing here, and then you get your equations of motion. I like this. This is just the general recipe. I mean, it looks complicated, but again, the whole point of the general recipe is to make it more mechanical and less cumbersome to decision making in a computer. You just want to give the same thing each time, like the same computation of kinetic energy and potential energy. I think this is the last slide that I have. Yeah, so this is the last one that I have. So do you have any questions or do you want me to go through some of the math here and more, or do you think it's better that you just go through it and then you post on Piazza where you got stuck, and then we can see how to help resolve it? you might want to just handwrite it and take a screenshot instead of using the latex because it could take a while to write things out. All right, so to summarize, we covered some dynamics. So I think next week we'll cover more about this, like how to, like maybe more examples of this and more about like how is this implemented in a computer. And one thing I do want to cover, like some common simulators that are used in robotics right now, like common robotics simulator that like my lab uses a lot, and how to do like learning from simulation, and then you can deploy a robot in the real world by doing like by learning in simulation. Then yeah, after that we'll have the more like common topics that you need to know over a robotics course, like 3D representation, geometry, and stuff like that. And then yeah, final exam review. We're almost to the end of the semester, so yeah, I think that's it for today, and I will see you on Monday. So thank you for being here.